morning, everyone. My name is Koyena. As you can see on the slide, today I will be talking about the paper that my colleague, Mr. Sridhar Adepu, my supervisor, Dr. Jonathan Go, and I have written based on the recent findings that we came across at a project in SUTD. So, before I introduce the project in more detail, I would like to give a short backstory on how it began, or at least for me. Well, I am a high school student of Global Indian International School, and I basically came into this research field by requesting for an internship at ITRUST Research Center. At that time, I had never really known that I had never really thought of presenting a research paper, let alone write one. Nevertheless, once I finally got the internship, my task was to find a novel way to detect cyber attacks on a cyber-physical system. That leads me to introduce the objectives of this paper, that are: what is the procedure to automate the generation of invariants in a cyber-physical system? How do we verify the accuracy of the invariants generated? It might sound a bit gibberish, but hopefully by the end of the presentation, everything makes sense. So let's start with cyber-physical system. What exactly is it? So a cyber-physical system is basically a combination of physical process, computation, and communication. It is used across various sectors from energy, water, transportation, to manufacturing and healthcare. So it's pretty important, this system, and that's why probably it attracts many potential attackers. From cyber criminals to disgruntled employees, these people infect these systems for their personal gain. In 2006, for instance, an attacker compromised a computer at a water filtering plant in Pennsylvania and used it as his own distribution system for spam and pirated software. Therefore, to improve the security of such systems, SUTD has many test beds, wherein we worked on one known as the Secure Water Treatment Test Bed. As you can see on the slide, there is a diagram which illustrates the process of the system. There are 6 processes. It starts from raw water input to reverse osmosis and backwash. There are also quite a number of sensors and actuators. There are 52 of them. Obviously, before I came here, there were some researchers like Sridhar who used invariants to detect cyber attacks on the system. Now, invariants are basically conditions or rules that can be relied upon to be true on the execution during the execution of a program. These researchers try to find links among physical and chemical properties that of the process controlled by the PLCs in the CPS. However, to identify these invariants, it takes a lot of time, as they are usually done manually. Therefore, during my internship, I tried to automate this process. I came across a term, association rules mining. It's meant for finding frequent patterns, associations, correlations, or causal structures from data sets. There are many types of algorithms for this mining, but I chose to do a priori algorithm as it's easy to implement and understand. So the data I used was collected continuously for 11 days. During the first 7 days, the SWAT operated normally, and during the remaining 4 days, it was under attack. There were a total of 36 attacks launched during the data collection process. It ranged from single point attacks to multiple point attacks. So in total, we got around 1 million samples, which were divided into 2 data sets, one for normal and another for attack. So I use both these data sets. I use the normal for finding the constraints and the attack data set to implement these constraints and find out how effectively they could detect the attacks. The way a priori works is that it finds the frequent item sets before it generates rules. Now these item sets contain sensor values. So according to the system we worked on, our item sets were FIT 101 high, FIT 101 low, P101 on, P101 off, and so on. To find frequent item sets, there is a value which we needed to type in. That is minimum support value. Now, let's say you want those item sets to have a min support of 0.3. The program will return those item sets that frequently appear 30% or more in the data set. Now you have found the values, all the values that appear frequent according to your min support. To find the rules, to generate them, there is another value which you need to type in, that is the minimum confidence value. This is the indication of the minimum number of times you want the rule to be true. For instance, if you set your minimum confidence value as 0.9 and you have a constraint that says FIT 101 high should give P102 off, the program will search for all FIT 101 high sets and will calculate how many of them have P102 off with it. In the normal data set, the constraint's confidence is 1. That is, it's 100% true, that is, it's true all the time. Similarly, I found other constraints. If I asked rules with any confidence values, I got around 11,500 rules. For confidence values 0.9 and above, there were around 7,200 rules. As shown on the, just to read out a few examples, as shown on the last line, last row of this table, LIT 301 low gives P101 on. That is 95.7% true. Another one, if MB 101 is open, FIT 101 gives a high value. That is 100% true. So, once I found all these values, we then compared with the invariants that were identified manually. Just for better comparison, I've kept both the tables side by side. So as we can see, the first rows of both the tables say that if MB 101 is open, then FIT 101 is high. Similarly, there were other rules that also matched with the invariants that were found manually. However, like most solutions, there were challenges while implementing this. So when I combined these rules and implemented them in the attack data set, in the first 7,000 rows of the attack data set, we got a lot of false positives. The predicted value said that there was an attack, but the actual label said it was normal. The reason why this happened was because the processor the system was in a transition state. Now when the system is in a transition state, there is another set of rules that are applicable to it. But if I were to put those rules, if I were to implement those rules for the rest of the data, I would get a lot of false negatives because those rules are not applicable when the processor is not in transition. Therefore, that led us to find what shall we do in the future. We indicated that we can perform a time series data analysis and computationally figure out how long does it take for a processor to get out of the transition period. We can then train the data using using the results we find along with the rules we initially found. Then we can test it on the attack data set to see how accurate and precise the attack detection is when we use this method of constraining data. So that's what we basically talked about in the paper. We tried to figure out the effectiveness of association rules mining for invariant generation in cyber-physical system. Thank you so much for staying with me till the end. any of you have any questions?
Thank you very much. So my question is, so how many new invariants did you find, in fact, with your method?
Okay, so technically, when they manually found it, there were a total actually of 6 for like particular processor and all. But then since these rules which we found were actually like for one sensor to another sensor, that's just like between 2 sensors. So that we got around, if you want to tell like a confidence value of above 90%, that was around 7,200, and so just minus 6 and that much of new rules we got.
And do you have the feeling that there's more invariants out there?
I mean,
or is it complete now?
huh?
Now, do you have the feeling that you have found everything? Or are there more invariants there to be discovered?
I mean, there could be more, but then till now, since there's like so many rules, and the thing is, not any of them is false. It's just that it depends on what stage is the processor in. So it just depends on the processor, and then the processor stage, and that's where we put those rules accordingly.
Okay, thanks.
You're a high school student?
Yes, I'm a high school student.
I'm starting to doubt that, the calculus is a required course for anyone, but thank you for your presentation. Did you have any chance to maybe collaborate with the researchers? 7,000 rules is not going to be particularly helpful because there are just too many. How many of them were actually deemed to be useful or appropriate for deployment in the system and monitoring?
Okay, so like I said, when we try to implement those rules, we first focus on the first 7,000, otherwise the system would crash. So during the first 7,000 rows, only I believe the processor 1 was only attacked. So we constrained further of those rules to just those which were related to P1 constraints. So it just depends on what processor we're looking for, and then we give those rules in that relation. Yeah.
Thank you. Knowing what you know now or have learned, why in the future works you haven't considered the processor transitioning issue resolution?
We did the time series data analysis. Over there, we would find how each of these transitions really went and how does it occur. So that's where we will try to figure out. So like for instance, if let's say in the first 12 seconds that's how long it takes to start, then we will have this kind of algorithm which will say that, okay, for the first 12 seconds, these all rules would be applied for that. So that's how we're going to do it.
Will that reduce the number of false positives and negatives for you?
Yes, that's an hypothesis. Yes, it should be.
See, to me, that should be a question to resolve as part of the strategy for the future works, because it won't go away. It'll become more confusing for you, would it not?
Yes, it would. So.
Okay, I won't badger.
Okay, thank you very much. Let's give a big hand to Koyena.